Okay, welcome to CE 5700. So this is lecture 4, site response analysis. And for this part of lecture, there's two parts. First, we will talk about soil dynamic properties, which is essential for the site response analysis in geotechnical engineering. So here pretty much is we step back a little bit, talk about the fundamentals of soil properties. And in a way that this is brand new because our previous class, including like your foundation design at undergrad level, and also we went through 566. If you have taken 566 with me, we talk about the soil mechanics. But those soil properties that we have mentioned before, those are under static loading. Nothing about dynamic loading. So the difference between static and dynamic loading is for dynamic loading, you have the cyclic events, which means the loading will go back and forth. You can think of a sine wave. For static loadings, pretty much it's just like a monotonic type of loading. You're adding a dead weight on it, on the soil, and the loading will only go one directions. But in earthquakes, it's kind of like a cyclic loading. You think of like again like the ground motions that you have play with in lecture numbers 2. So the ground motions will travel through your soil elements. So pretty much you have a cyclic loading going back and forth, and you will be greatly affect the type of loading. Will greatly affect the soil properties. Okay. So just a quick reminder where we at this point of this semester. So I think this is easier to see with a eraser, right? Oh, this is not bad to ponder. So this is where we at. We mentioned about this class pretty much is try to follow the path of the earthquake. Lecture 1, we talk about the kind of like from the seismology standpoint. So when earthquake happens, it's kind of like release of energy or release of stress that happen at the pattern, the plate of the earth crust. So you release earthquake happens, you have already built up enough energy, and at some points it's high enough that the earth plates cannot withstand anymore. So you kind of like corruptions and and release a lot of energy, and then like you travel through all the bedrock, and then you go to the soil. So this part is for the seismology, and getting to the soils is the geotech. And the seismic site response analysis is start to talk about when the earthquake release at the bedrock level. So the earthquake that happens here. So you have kind of like a ground motions, or like actually when earthquake happens, it will be like a release of energy, right? So you have like a lot of like propagations of side wave. So here and after going through the soil, would it be like amplified or de-amplified? So that is the site response analysis. And throughout this like amplifications or de-amplifications, you will require to understand the understanding, or like through the analysis, you need to have the input of the dynamic soil properties. So this part here pretty much is what we will talk about in this lecture. The site response analysis, and we require we need the small string. So throughout this lecture, well, it'll be better. So throughout this lecture, you will hear this term or not. So in order to do the site response analysis, we need the dynamic soil properties, which this is happen at small strain. So we would hear about this term a lot, and I'll explain what is it in a better details. So this is strain, is kind of like a source, a small displacement. So this matter a lot on how the shear wave again propagate through the soil. Okay, so when we talk about soil behavior or soil properties, one very important aspect is to understand the soil stress strain behavior. So which is, we talk about it already when in the static under the static loading from the previous class. So for example, remember, like, when we do our foundation design, for example, you have some sort of loading, could be from a structural load passed through the foundations, and you're adding the bearing pressure to the soils. So you can imagine, like, you create kind of like a slip surface when we try to mobilize the ground. So we want to know, like, how the stress is cutting through the loading passing through and soil elements. So the loading here is kind of like providing, like, on this piece of soil elements, you're providing kind of like a shear force, and this shear force adding on our soil elements, right? We have a loading trying to deform the pieces of the soil, and I'm extracting the deformations. The movement's supposed to be small or being progressive, but if we look at, like, a time slot a failure, so the amount of deformations here is kind of like the string part. So this is displacements, and the stress is the loading. So loading is come from any construction activities, like this time, like maybe from the foundations, and passing as to the soils. So you kind of like a shear stress. And for this particular piece of soil elements, we know the original heights. So the height of these the soil elements here, and we define the strength, the shear strain here is the amount of deformations divided by the height of the soil elements. So the shear strain, which is the letter gamma here, the Greek letter, is the amount of deformations divided by the height of the soil elements, and then times 100%. So that will be your shear strain. And we have the loading. Again, the loading is tau. The shear load when we get on the soil elements, there's a shear stress. So the shear stress is inducing the deformations. The deformations can convert to the shear strain, and this is deformations dependence behavior. So that's why we call this as a stress strain relationship or stress strain behavior. Is the shear stress will be a functions of the deformations or the shear strain. So that's why we get the stress strain curve. So remember, like, if you have taken the lab class, you have seen the direct shear test when we load on the sand samples, and you record the loading, right? So you kind of like cranking the shear device. You give your shear displacements or shear deformations or shear strength, and the load cell will pick up the shear load and divided by the area. You will find out the shear stress. And in 366, sorry, not 366, the 566, when we talk about soil mechanics, We also talk about the stress path in the PQ terms, and it will tell you how the stress path look like, right? If this is like a loose soils, we talk about all this in 366, 566, and then like this is we talk about the critical state soil mechanics, and this is the critical state line. So this is the critical state line with soil friction angle there. So that will be the soil mechanics part that we talked about before, when the soil is subject to a static loading. So what happened in earthquake? Earthquake is not providing like a static loading, but you provide a dynamic loading. So when earthquake happens, it kind of like a upward propagating a shear wave. Let me just screen maybe. So you will be when earthquake happens again. It's just like the earthquake ground motions record they play with in lecture 2. So those upward propagating shear wave will travel through your soil elements. So instead of just like a static deformations that the soil elements will the soil will experience, in fact you will go kind of like a back and forth. So so you kind of like a sine wave going through the soil elements, and you will go back and forth. You will go like deformations can go one way, and then like another. When you like reverse the loading, you can go the other ways too. So it's kind of like going back and forth, and you will creating like the displacements here, back and forth, right? So this is still the deformations, but you will have at two different directions. And we still have the same, for example, we still have the same soil specimen height. And this is now like again the upward. So this is still the upward propagating shear wave. That is adding on the generate from the earthquake. So in terms of the stress strain plot, again, like everything ties back to the stress strain behavior. And now since this go back and forth, so it's not like going one direction only. You can go both positive and negative. And again, this is the same thing. This is the shear strain induced from the shear displacements. Could be like from the positive side and also from the negative side. And this is the shear stress. So you imagine like actually the loading adding on it will be so this is the soil, right? This is kind of your axis, and you can kind of like go back and forth like a sine wave going through it. So you could have your positive loading, and you can also have your negative side of loading. So the stress strain plot will look like this. First, you will go positive on the stress, so this is the positive part, and then you generate positive deformations. And then like you go up, go down, and then go to the negative, and then you would generate like a negative displacements too. So this is kind of like the hysteresis loops for the stress strain part under cyclic loading. And this is at kind of like assume this is your first loading cycle, and then there with a bunch of different loading cycles going through your soil elements that you're looking at. And then like at as the more loading go by, the soil start to fail, and then we generate more and more displacement. So you imagine this cycle, this keep going back and forth, and the loops or the hysteresis loops there will become larger and larger. And at some points at failure, you will have a high displacements. So you could have a loops something like this. You're generating a huge amount of displacements. So that would be the shear strain at a higher shear loading. So this is kind of like the stress path for static loading here, and for cyclic loading, again the same PQ port, and now this will go back and forth. So this could be your first cycles, and then you will be keep loading it, and then realize this is the mean effective stress, right? The P is equals to 1/3 of sigma V pi plus 2 times the horizontal stress. And as this can go very deep in soil mechanics, but this is earthquake engineering class, so I don't want to go too deep into soil mechanics. But if you want to understand more about this stress path, you feel free to come above. Feel free to stop by my office hour. So the stress path here under dynamic loading could be a little bit more complicated than the one that you learn in 566. Everything is based on static loadings, and definitely this topic here we talk about here is getting to the PhD level. And this, we can spend a couple weeks just talk about dynamic soil behavior, and this kind of our scope of the geotech earthquake class. So here I don't expect you to know too much about it, about the stress path under the dynamic loading. But what I do need you to get out from this is the big picture, all the transitions from the static loading to the dynamic loading. What kind of loading on the soils elements, and what did you expect to see? And the stress path, if to complete this, you will keep loading until you fail, you lost all the vertical effective stress, and then you will start to see the butterfly loops. So we see a lot of this in the laboratory teller of the cyclic loading. And this slope here, actually, this is the critical state line. So this here, the slope here is give you the friction angle, and this critical state line here pretty much is supposed to be the same as the slopes, the same as the one that you obtained from a static loading, the same stress path. So this is kind of like a quick picture on about the dynamic loading, or the dynamic stress ring response when earthquake happens. And for our applications, we want to do site response analysis, which means we need the main focus is to try to get the soil dynamic properties. And for the case of earthquake loading, the most important soil dynamic properties will happens at the first loop at the stress strain curve. So next we'll focus on looking at on this first stress strain loops. The next time we talk about that, kind of zoom in to talk about what kind of informations we can recover from that first a stress strain loop to establish the dynamic soil properties for site response analysis. Okay, so this is a zoom-in picture of the very first loop that we talked about previously. So this is the hysteresis loop during the cyclic loading. So this hysteresis loop is pretty much the first one at very small strain. because this is the very first one. So the displacements that induce, so the deformations that we talk about here will be the pretty much the smallest as possible. And actually, there's a lot of informations about this first stress strain loop or hysteresis loop, however you want to call it. So this loop come from a couple of different parts. So imagine this is your loading time history. So if this is time, so if the this particular sine wave loading here, this is time, and the x-axis is time, and the y-axis is the shear stress. So what I'm trying to refer here is this loading cycle. So you have the shear stress, and then with time, this loading cycles act like a sine wave. So just like here, it's just like a sine wave. And this sine wave kind of come up with four parts. So first, you have your very first loading cycle or loading part. So it kind of the shear stress go from positive to a peak. So what does it mean is you represent the very first part of the loading, because prior to the loading, we're at the 0 positions. So that's before earthquake happens, right? Everything stayed there. There's no shear stress and no shear stress, so it's not inducing any displacements or shear strain. And now the earthquake happens. It's kind of upward propagating shear wave. So it act like a sine wave going through your soil samples. And the first a quarter of the motions is from 0 to the peak, the positive peak. So this is the 0 again, and then the loading will induce the peak of the shear stress. And then what we call it has a stress reversal. So now this will be a go down. So there's a little bit a reversal go down. Try to use a lighter color. But anyways, so this is the reversal part of the loading. Oops, actually it didn't go through the negative. So it kind of stop there. So this is the reversal part. And then this will be extend into the negative numbers, right? So this will keep going. And then finally, you will go back to the 0 positions for this particular sine wave. So do this part right here. So eventually, this stress reversal will go reversal. We'll go back to the 0 positions. And then here come the next cycle. So what happened is the next cycle. So earthquake motion is a lot of random pulses at different frequency and also loading amplitudes. For simplifications, we will model it as a series of harmonic motions, which means you have a single frequency and single amplitude. So you kind of just a repeating sine wave. So we talk about this more in solid fractions. But in fact, in real earthquake, it will be a series of random pulses with different amplitudes and also frequencies. So this is more like an earthquake loading. So but now we just simplify it as a series of uniform amplitude loading. And then you finish your first cycle, and then the next cycle will come in, and the loops. So the next cycle will come in, and the loops will get larger and larger. Will get larger and larger until the soil fell. So that is the very first loop. So we are looking at the first hysteresis loop, and from this first loading cycle, or first this a loading soil response, will give us a lot of informations. First is the the beginning slope, right? So we just talk about the yellow part, the very initial loading. This initial part give us the a straight line over here, and this straight line, the slope of it, we call this the Gmax. So Gmax is a super important parameters for our site response analysis. So the G is stand for the shear modulus. So G there, so G in general stand for the shear modulus, and Gmax it stand for the shear modulus. Because again, like the loops, there's a lot of different loops as this the loading going back and forth, and the very first one will give you the greatest slope. So because like this you, as you can see, the loading cycle get larger and larger, and then you get more flat on the slope, because this go back to 0, right? This go back to 0, and this pretty much like after that you will have your second part already. So this is the second part of the loading already. So this is the second part of the loops already, and then as you can tell, the slope will get flatter and flatter, and you will have the greatest slopes at the very initial part. So this is the most stiff response of the soil. So that's what we call the Gmax, at the smallest shear strain. And shear strain mean like the smallest displacements. So this is the Gmax stand for the shear modulus of very first loading cycle. So that's the Gmax. So the Gmax is pretty much just the, one of the most important dynamic soil properties. So this is super important, and it's also important that you understand where it comes from. So Gmax is the maximum shear modulus, which comes from the very first hysteresis loops loading from under any form of like a cyclic loading on soil. So that is the shear max. And another point here is the very first loop, the maximum point you're hitting there, the string level, the shear string level, we call the gamma C. So the gamma C here is the so the gamma C here, what we call is the cyclic threshold, which is the boundary, between elastic and inelastic behavior. So after like your first loop, you start getting into the elastic range, and we will talk more a little bit about that. And this part of curve, so again, like start from the very initial part, and then like so you start from the very initial part, you reach your turning point, and then that is your cyclic threshold, and then you will go to the reversal, and then this part of curve we call it a backbone curve. So it's just a terminology for the modeling people's how to call this part of the loops. They call it the backbone curve, and then like you will the loops will be like turn back and then go back to the 0 positions. And another thing is like we talk about a G And the other very important parameters for soil dynamic properties is the damping, and the damping is the area. So the area of the loops reflect the material damping. So the area of the loops means, like, this one, the area of your first loop. So the area here means how much energy of the material can absorb. And soils, like, if it's a soft soils, then, like, for example, it's a very soft clay, and then, like, you imagine, like, you can absorb a lot more energy than like a very dense or stiff sand, because the soft clay just like a cushions. You can take on the energy, absorb it, but the stiff sand, kind of like behave like very rigid. Just like you pound on like a hard surface, then the action and reactions you soon up you're feeling it, and to reflect the material damping, theoretical standpoint is pretty much just the area of this loop. So the larger the area, the loops here, the softer or the more damping is the material, and you'll be more non-linear. So and so to make it short, you could imagine the response of clay and sand could be very different. For example, if you have a very stiff sand or dense sand, the loops of the sand pretty much just, or even you have very high Gmax, so, it would be just like a straight line like there. So the area is very small. Whereas it's like a soft clay, the response of the first loop could be like very highly nonlinear and give you like a much larger area. So this could be like the response of the soft clay, versus this is like a very stiff sand. And the area again reflect the amount of damping that the soil can absorb. So again, like the whole picture is like we want to model how the soil properties when you experience like a dynamic loading, which means like an earthquake shear wave passing through it. And the very, very important informations is to look at the hysteresis loops, which means the stress strain response reflected on like the stress strain plot, and the stress strain plot. And you may ask like how to obtain this stress strain plot. The engineering practice you can imagine is take a soil samples, ship it to the lab, and then do it like a cyclic loading. Then you can recover the dynamic soil properties. So you can do it in the lab or you can do it in the field, and we'll talk about the field test later. So after this, we talk about the lab tests first, how to obtain those like hysteresis loops, and then we can also touch base on the field tests. Okay, so another thing about those hysteresis loops is you realize like this is also a strain dependence, in a sense that like when we have repeating loading cycle adding on it. So so this is, for example, this is the first like a cyclic loading. So you have the first loop, right? And then if this is the first one, so you connect the points between the origins. So you connect the points between the origins and the maximum point here. Then you get a straight line, and and that represents the slope of the line over there, represent the shear modulus. So if this is the first one, so this will be the G max. You're the first like a loading cycle. Then you have the subsequent like a loading cycle. For example, here now, then this is your second loading cycle. Then this is your second loops. So you see the sequence of the stresses, like you go this way. The stress strain curve developments is you form the loops and then complete the loops, then you will stay on, and then you will have your second loops. And then as you can tell, the loops just get larger and larger until like you have enough deformations and the whole soil fell. And the subsequent hysteresis loop here, if you connect the 2 points, again the origins and the maximum point here, then you get the shear modulus, and this is another point with a corresponding like a strain level. So again, like this is kind of like if we think about in time history, so time versus like a shear stress going through a soil element, and this is the representations of the stress strain curve. So this is your set. So each loops give you one G value, the shear modulus values, and so each one give you a pair of data. Again, you have the shear modulus and the corresponding shear strain, and then you have now the second loops. You have the second corresponding shear modulus and also the corresponding shear strain. So if we plot up a graph of the shear strain versus the G values, then we get a curve, and this is what we call the shear modulus reduction curve, which is very important. So this is the shear modulus reductions curve. So you will see like the shear modulus actually is going down with the shear strain. So that's why we call it reduction curve, and we need this curve to describe the whole soil behavior, the dynamic soil properties, the dynamic soil behavior. So one value, G max, great. Another G value is great, but you just like representing one soil response at a certain strain level. So you need to have the whole curve that describe how the shear strain, the shear modulus response in terms of the gamma, the shear strain. So this is the whole complete picture with the soil dynamic properties. So we need a G, and also we need a damping ratio. So we talk about the damping ratios more too. So this is the whole idea. So this is a very important slide to summarize, like what we are learning, or like the whole picture. So I would say this is the whole picture, of the soil dynamics properties. So if you understand this slide on like those like graph there, also with the how to use them, then I think you will be ready to talk about site response analysis. So we need like those like soil dynamic properties, understand it before we get into to talk about how the soil responds under earthquake loading. So this is fundamental to talk about soil behavior under dynamic excitations. So we talk about the G, right? The shear modulus, and we also very important concept. This G is not a constant; it's evolve. It depends on the deformations, which is the shear strain. So if we do this to plot a curve, the log of soil strain. So we'll see how the curve look like. So there's also a couple like terminology that we need to know, a couple concept. So out of this curve, well, first of all, like, the whole thing, the whole curve would behave something like this. And that's like a couple threshold we need to talk about. First, like a very important point is when the strain is very small, close to 0. And this particular point here, we call it Gmax. So it's from the first cycle at the very small strain level. So this is Gmax. This particular point is the Gmax. Again, when the shear strain is very close to 0, the very first loop of hysteresis loops, that the slope representing the stress strain response over there, it is the Gmax, the maximum shear modulus. So this will be the highest value. So it's supposed to be kind of like a flat line that maybe going down a little bit. So this must be the maximum point. And after that, like, this also represent the stiffness of the soil. So the more loading that you add on, so the repeating loading, you loading on the soil, you will kind of like a weakening the soil, which reflect on the shear modulus values. So you will have first of all, like, there's a couple like a different strain level. So first is 10 to the power -3%. We call this to be the elastic threshold. So between like 0s to this like shear strain level, the soil will behave like linear elastic. So you do all the loading and unloading, you expect like you go back to the original place, right? There's no like permanent deformations. Everything is still behave like elastically. And after this threshold, you will still be and between like 10 to -3 to 10 to -2% of shear strain, you will hit another threshold when you go beyond 10 to -2, and this threshold called cyclic threshold strain. And what happens here now, between the two threshold, the soil will start to behave like a non-linear. But it still behave like elastic. So which means like if you do the loading and unloading, you will still go back to the original positions. So if the cyclic loading go back and forth, like you're not losing any like a stiffness. And same as here, even though like you start to go non-linear. So this is supposed to be kind of like a straight line right there, and now you start to have the curve. But if you do your loading and unloading, you will go back to the original positions. But beyond this like a cyclic threshold strain, then you will start to have, so going beyond here, you start to have non-linear inelastic. So you will start to have the plastic behavior. So when the loading go beyond this like a deformations level, so you go all the way loading up to here, and you go back, you will have the hysteresis effect. So that will be not like going back to the original like soils like stiffness response. So throughout this like G over like a shear strain curve, we need to understand like what those like a threshold means, and also understand that like different soil type will give you different curve, different the soil from different project will also give you like a different like a modulus reduction curve. So that's why in a site response analysis, it's important to establish those curves. And we'll talk more about those. And you will see, like, when you want to soften a deep soil, you will need to select the right curve for your soil profile. So different materials, sand, clay, or gravel, then you will expect to use different Modulus reduction curve. So again, like, you come with two important thresholds. First is the elastic threshold strength. Is happen at about at a very small deformations of about 0.001% shear strain, and beyond this point, the soils will no longer behave linearly. And also, like, the other very important threshold is happen at 0.01%, and beyond that, the soils start to behave like inelastically, and you will start to have those like a degrade, softening effects. Pretty much like, you start to go into the failure point, or like, you never fully recover the soil strength after the deformations induced by earthquake beyond this strain level. And you could also expect to start to have volume change under drain loading, which means when you have volume change, which means like you may have settlement. So earthquake can induce settlements if the earthquake is strong enough to deform the soils beyond this like shear strain level. And pore pressure start to generate, which means like, if you have sand deposit, the strength of the soils is start to be decreased, and the worst case scenario, you can have soil liquefactions. We will talk about soil liquefactions in module number 5. So that is the shear Modulus reductions, and oftentimes we will normalize this curve with Gmax. So this Gmax, there's some like a laboratory or field testing procedure to find out, to measure. So after you know this Gmax values, what we do, it will be derive the whole curve with Gmax. So then you will get a curve, maybe something like this again, where the shape will be the same as like before the normalizations. But the nice thing about this is like now, since this is derived by Gmax, the beginning point here will have a ratio of 1. And for typical soils, the elastic threshold will happen about 97% or the ratios of 0.97 of a G over Gmax. So here could be like a 0.97, and here would be about 80%. So those are just like a rule of thumb. And different soil type, you can expect like something like gravel versus soft clay, you will have very different response. But just give you an idea on how the numbers look like. So those are the Modulus reductions, and corresponding to that, because again, like each hysteresis loops, you get a G, but you can also get a D by the area. We talk about next slide on how to calculate the D, but like pretty much it's the area of the loops. And for example, like kind of like each like represent shear strain or like deformations. You have a corresponding area of the loops, so which give you give you a graph to tell you how the Modulus, the damping look like. So what you do is like each corresponding strain level, you calculate the area of the loop, then you give you 1 data points. So 1 loops give you 1 damping ratio. So 2 loops give you 2 damping ratios, so forth and so forth. You keep like working on the loops, or you find the areas and the corresponding shear strain level. Then you can graph this curve. Then this curve will give you the damping curve. You will be the shape of the curve depends on the soil type, but generally you will get something like this. So this is the damping curve. And again, like you kind of like coupling with the Gmax, so you have the linear part. So if I do better jobs, is this supposed to be flat? So you have a linear part in the linear elastic regions, and then you start to behave like a non-linearly after that point. And the damping at 1% shear strain, this point will be about 20% of damping. And we will call this the very first point, corresponding to the Gmax values. This is the D mean, the minimum damping ratio. And it's also like again a function of the source strain, the shear strain. So we will need both the G and the D to describe soil response under dynamic loading, and we need those two curves for site response analysis. So speaking of how to calculate the damping ratios, so that's a method to do it. It's like, for example, each loops, the damping area, the damping ratios will be equals to the area of the loops divided by the area of a triangle right there. So the triangle, the area of the loops is a little bit hard to calculate. You may need some like coding techniques to do it. The triangles is easier because you know this point. So here, this point here pretty much is corresponding to the maximum shear strength of the loop. So you know this length, and you know the maximum shear stress corresponding to the loop. Then it's just the area of the triangle. And the damping ratios, again, is kind of like from an energy perspective. And the damping ratios will be equals, the formulas will be equals to 1/4 pi times the energy that being dissipated divided by the energy of the strain. So which means the dissipated energy is the area of the loop divided by the energy of the strain, which is like corresponding to the largest strain over there, will be the area of the triangle. And substituting the formula for the area of a triangle, this formula can be simplified by something that we know, like the shear modulus of this curve. So this is G, and then times the corresponding to shear strength of this loop. So this is the strain level of the loop, and we still need to calculate the area of the loop. So that's how we calculate the damping for one cycle at a particular corresponding like a strain level. And we need to do this like for all the loops that we obtained. So those loops and those data could be obtained from the lab. We talk about the lab testing. So we collect soil samples and ship it to the lab, and then like induce cyclic loading on the soil samples. And then you generate all these loops, stress strain curve. Then you can come up with the shear modulus reduction curve, and also the damping ratio curve that you will need for seismic site response analysis. Or you can do a field testing too. So you will apply like cyclic loading to the field, and then you will measure the data.
Okay, now, so the question is how to obtain those reduction curve, both modulus reductions and also the damping ratios curves. How to establish them? Because end up you will need those curves for your site response analysis. You can nowadays those practice site response analysis. And during practice, we'll be using two popular softwares, either the Shake 2000s or maybe like a newer Shake model. But this class we use deep soils. We would also talk about deep soils at some point for this lecture. So before we use those site response analysis program, pretty much we need to have those shear modulus and damping ratio curve ready, so such that we can perform our analysis. And there's a couple different ways to establish those curve. First is using some existing curve which have already been established based on a huge database. So there's some researcher either pass like seed and aegis. So aegis is the same aegis we talk about. He started his academic career as a PhD student at Berkeley, studying with seed. So again, seed is the father of geotechnical engineering. He was like a long-time professor at Berkeley, and then he passed away in 1989. And his son also, this is like Harry Bolden Seed, and his son Wayman Seed also was a geotech faculty at UC Berkeley. But Wayman Seed retired already, and the senior Seed he passed away in 1989. But the geotech earthquake engineers pretty much start from seed. So the long time history, maybe we start from Tosagi in geotechnical engineering, and then he has a great geotechnical engineering master program at Harvard, and that's where Casagrande was his first students, and he influenced quite a few of very significant students, and Seed is one of them at Harvard. So Seeds established is kind of like a pioneer to look at this issue, and then he established a few curve for engineer to use for the analysis, and also Seed established the long non-linear equivalence site response analysis, which we will talk about that too. So pretty much he did a lot of work in this subject. So those seed curve is available. In my opinions, they may be a little bit outdated, but it will be a good starting point for us to learn. And the Wusentate and Adobe curve is also very, very useful for clay. So those curve I have already uploaded on Canvax. So if you look for the files that say degradation curve, those are where we come from. So this is the Seed 1984, and be very careful. Those curves are very material dependent. So for example, this curve that you can use is used for gravelly soils only, and this is a damping ratio curve used for gravels. So how Seed established those curves in the early days is based on the laboratory data that he had. So he won a lot of either Western column tests, or we'll talk about the lab tests later on too, or other field tests may be available, and then based on different case history, then he tried to establish the curve based on the soil type. So it's quite a bit of uncertainty, as you can tell, and it is not site specific. So you get some soils from California, some soil maybe from somewhere Midwest, and some soils even from Japan, and they put together as the database. Is useful in a way that is a good start, or you're working on a project that you don't have the budget to one site specific testing, which is extremely expensive, and not many lab in this world able to run those resonant column tests for you. And luckily, our research lab at Cal State LA, we do have a resonant column device, and perhaps we are the only one that to have it in Southern California. So it's a very rare device, and even rare is you need to find the right personnel to conduct those tests. So it's not easy at all. Pretty much is the most complicated lab testing you can ask for in geotechnical engineering. But anyways, like those are the curve that we have for the seed gravel, and realize like the shear modulus curve, those is done in a way that this is G over G max. So this is G and normalized by G max. And in the early days, like because of the limitations of the equipments, so the G max level may not be go as small as like a string level may not able to go as small as like we can nowadays, but it's pretty impressive. Like back to the 80s, even 70s, that they can have that kind of like a small displacements measurements. So this is for the gravels, and this is for the sand. And again, you see like there's a range over there. So when you use those curve, you need to be very careful. And actually, like how to input the curve on in your software package. And so again, you see how in the early days how seed and aegis they compile all the data and then come up with the range of the damping ratio. So damping ratio is even harder than the shear modulus. And this is the work from Wusentek and Adobe. So Wusentek, he is the long-time professor at UCLA. I think he just retired maybe 3 years ago, something like that. He got some training at Norway, NGI. So we talk about NGI too, in the laboratory. And actually Wusentek, he is the advisor of our Dr. Professor Mark Tuvengians. So he has been practicing in Los Angeles for a long time. But anyways, this is his work to come up with those clay curve, both shear modulus, and again, like you represent a G over G max, and also the damping ratio curve. And this Dalendelli and Stokey 2001 curve, those are empirical model. We talk about empirical model. And Stokey is from Texas, and he is again he is still working. He is one of the I think one of the academians is that he will work until the day that he cannot. So he is maybe almost 80 years old, maybe even like over than 80 years old. But he makes significant like contributions in this topic, and he earned the Tosaki Award in 2001. Because based on the contributions that he had on this solid dynamic properties. So he was my professor at Texas Austin too. But anyways, like those are the clay curve that you can use, and more curve for the sand. Again, try to compare the Stokey model with the sand and Idris. And this is the gravel that curve that we looked at earlier. A little bit comparisons over here. Actually those are some correlations. We talk about that later. And this is again the clay curve, the same Wusentek and Adobe clay curve that we saw before. And this is a little bit more in details. Also shows you like the PI values. So they are Wusentek, he made great contributions by establishing those curves. And when you select which curve to use, highly depends on the your clay properties, the parasitic index, and the OCR values. So those are another reference. So pretty much like if you are like a spectrums on different like soils, how the shear modulus would change. So highly soil dependent. So you compile all the data with the clay, sand, and gravels, and also the damping ratios. Again, over there, nothing is like a site specific data. Those are kind of like a curve that you can use when you don't have the budget to do a site response. Site samplings, and then like you want those expensive tests. So And your project, the semester project, pretty much like, you will pick those typical soil curve. And these files, I also give you a little bit more details on the Stokey model, on how to establish those like empirical correlations on those G over G max, and also the Dampened Ratio. So he has a lot of resident column data, because Stokey has a very well run lab at Texas running resident column tests, and he got a lot of project from nuclear plants around the United States. So pretty much like even like in the past a couple of decades, like any nuclear plant projects, you will go through Stokey on this dynamic soil property characterization plot, and he compile all the data. He able to establish the gradation curves, which earned him the Tsaki Award in 2001. So more of his models. So I upload those files on CanFax, so you can take a look. And in your use, you will becomes the options in deep soil. So this is the software of deep soils that you will use. Maybe like on a separate videos. On this lecture, I will walk you through how to use this software. But end up you need to use this software for site response analysis. Here, I just want to show you like where the selections of those gradients and curve will come into play. So at steps 2, later on I'll explain all the steps. And this is your soil profiles, and I just load and default examples in the software, this is the I think is Bay Area site. I forget which one is it, but this represents a real soils soil profile for a site. It's very detailed. You have like 53 different soil layers up to the bedrock level, and each soil layers you could select like a different like gradation curve. So if this is sand, layers, you could select those that we just talked about, like the seed at each one, the mean, the upper limit, the lower limit, or the amount, and maybe some newer models that like also come out like in the recent years. So you can select those, and you will load up like how the G max and the dampened ratios change with the strain. And it shows you the G max, and also the dampened ratios, and also the estimation of soil strength. So it's pretty handy. And so this is like those default soil type, and if you are running a very expensive project, like you're able to run some lab tests. So the price I would talk about here per test, we'll be talking about like 100K, or maybe like if not 100K, then will be 50K per test. Plus soil sampling, and also paying your lab to run the test. It's not cheap at all. Or like especially if you have deep soil samples, it's very expensive. So if you want to like have lab data, you can choose to user defined, and like you can manually type in your site specific data right there. But your semester project, pretty much like you're going those two. So back to our presentations. So those we talk about this, where this like a typical soil type dependence curve come from, and also the empirical correlations. We touch base on them. Those Stokey models, and very popular. So you can use those, which is you have more control in terms of changing the shape of the curve based on like you may have some very specific soil parameters, like the mean effective stress, and the PI, the OCR. Those you can measure it and then plug into these equations, and able to find the more calibrated, put it this way, more calibrated empirical correlations for the G G over G max and or whatever, G over G max and curve for the damping ratio curve. So I would say, like, the degree of effort increase go this way. So the degree of effort here, so you have different options. You go that this way. So the more you go down, the more expensive it is. And field testing, that's very important too. So field testing will allow you to get your G max or D mean, but you cannot get you the whole curve. We talk about how to incorporate the field data with the lab data. So if a very super important project, or imagine maybe something like a high-rise building in the downtown Los Angeles, or in the nuclear plant, or maybe some very important offshore geo platform, those you will conduct those, and usually they come together because you are spending the money anyways for field tests. Usually it's the project size, you can also afford the lab tests. And these two test thing will come together and give you the best chance to get the most precise gradation curve, such that when you perform a site response analysis, you can use the user-defined functions to input the site-specific data for your project. Since it's academic exercise, you guys will pick from those from the typical soils. So lab tests, the field testing, you have the causal and downhole. We will talk about that too after lab tests, and also the surface raise method. And I have uploaded the ASTM standards for downhole and causal testing, so feel free to download it and read more about that. And this course, when I was at Texas, there can be one graduate level class the whole semester. Stokey, we just talk about dynamic soil property characterizations. But this class is a general, that class is on top of the geotechnical earthquake engineering class. But this class is, it's a typical geotechnical earthquake engineering class, so we don't have the time to go into details. Feel free to read about the textbook. I think the Kramer textbook, Kramer did a very good job on introduce you those background on those field and lab testing, and in addition to that, if you read those ASTM standards, maybe do some research on your own, and feel free to stop by my office hour, and if you want to learn more, and then we can talk more about that too. But the basic idea here is I want you to learn this how to obtain those G and D curves, what type of options are available, and based on your need, which ones should you go? Those will be the first step, when you work together. So for the dynamic lab testing, there's many different kinds, and I have list of 4 typical testing. So the bending elements is just only give you the G max one measurements, but the other 4 it can give you the whole curve, whole shear modulus reduction curve and damping ratio curve, which means the test is scalable to test at different string level, such that you can get the corresponding G values. So you have the cyclic triaxial, you have the cyclic simple shear, and the cyclic torsional shear, and the resonant column. So the torsional shear and resonant column, usually they come together in the same device. And cyclic triaxial is the most simple one. I think at master level, if you work in the lab for your master thesis, very likely you can work for a cyclic triaxial project, and getting simple shear is that simple shear is not simple at all. But anyways, you will start getting into PhD level, and for research. So for very sure, if you work on the topic of resonant column, you'll be a PhD research topic. But anyways, one of the key difference for those laboratory tests is this again is a shear strain level. So you will see the resonant columns is so special that you can go to extreme small strain. You can go even up to to a degree of -5. 10 to negative 5 degree of precision on measurements instead of the shear strain. And triaxials and simple shear, those have the larger strain. So remember, like even though you're doing the static and static tests, you do a compression test, compressor triaxial test, you get a stress strain curve. The precisions of the stress strain curve, the lowest you can get is down to between 0.01 and 0.1%. But the resting columns can go way more precise than that. Okay, so let's go in a little bit details how to use the combine the lab and field data. So this is about combining lab and field data. Oops. When you do the dynamic solid particle characterizations, if you can only afford one test, you will do the field test, not the lab test. So pretty much like in practice, if you want to make your lab data useful, you need to have the field measurements. So repeat one more time. It's very important that you understand this point, because like a soil samples, you have all the disturbance, and even though you got a perfect hands, you got the perfect labs, and you got the perfect data, the soil samples itself have all been disturbed. So whatever you measure is not well reflect the in situ conditions. So that's why you will need the in situ field test to correct your lab data. But the field data is only limited to one measurements. You only can give you the Gmax and the D mean, which means like you cannot like change the or like have a very well control on like a precise measurements on how much deformations you are, but you can do in the lab. So in the field you only can do the test that there's no like a displacement at all. So you are getting the Gmax and D mean values. So now in the field you have the Gmax and D mean values, and in the lab you get like the shape of the curve, and you will use the shape of the curve combining your field measured like Gmax values and then to do the corrections. So the examples is kind of like here. So first, like the big picture is all the lab tests. They are affected by sample disturbance and sample preparation method. So the small string dynamic test results are particularly sensitive to those factors. The concern is not as high when you're doing a standard triaxial test, because again the string level are different. And when we do tests like resting column, we're down to like an extremely small string. At that case, like you magnify the problem of soil disturbance. So that's something that no way you can get rid of it. So Geotech understand the big picture and the consequence, and they come up with solutions to to get around with it. And to do that, is combining the field data with the lab data. So pretty much like, for example, this is kind of like the lab measurements, and you get from the lab. So you will like normalize the whole thing with the Gmax already. So you can normalize the curve, and then like after that, you will multiply that by the field measured Gmax. So pretty much that you kind of correct the curve with the field data. You will bring up the curve with the soil disturbance that you may have already. So that way, you can correct for the data. So the procedure is, first you will establish the normalized lab shear modulus curve, so the G over Gmax, to determine the shape of the nonlinear behavior. And then like the field measurements, we talk about like the downhole and the causal, like at the end of this presentations. What you get will be the shear rate velocity values, and this equations here,
the shear modulus equals to density times the square of the shear wave velocity. This is our theoretical equations that relate the shear velocity with the shear modulus. So you can measure this and you know the density, then you can find out the G max. Because the shear wave velocity that we measure is at the very small strain. So this is corresponding to the shear strings is almost equal to 0%. So this corresponds to the G max conditions. So that's why you can calculate this G max. From the shear wave velocity, we get the G max from the field. So end up like how we correct for the whole curve is we try to multiply this curve that we established in the lab by the G max that we obtain from the field. So we pretty much like you will bring up this lab curve by the field measurements. So we will use this for practice. We'll use this end up like we will go into your user-defined functions in site response analysis. So we will talk more about the site response analysis. So this lecture has 2 parts. So we will spend like a lot of time after this to just talk about site response analysis. I will give you the background and also like how this the math work behind the software. And your semester project, you will be doing this once on your own. But anyways, how we get the to combine the field and lab data. And for those tests, so we just try to touch base a little bit on the different testing procedure. First, the cyclic triaxials is supposed to be the most straightforward one. So cyclic triaxial is just like your standard triaxial, but now is the cable, the device that you have. We have one in the lab, in our own lab, but the capability of it now is like it's not just like a static loading. Remember, like your compression test only go one way, and then all the tension tests only go the other way. But the cyclic test is able to go back and forth, either with like air piston systems, or like or hydraulics or electromagnetic system that like have control. And the STM standard I also upload on Canvax. They will specify on what kind of control that you need to have, down to the positions for generating those stress history. So this will be your input stress history, so going up and down on the soil samples, and then you will have the corresponding pore pressure that you generated. So you have the sensor over there connected into the soil samples to measure the pore water response, and also the axial strain. So you will have the LVDTs, there to measure the displacements. Then you can monitor how the if this is a low control test, which means like you input a soil stress, and then like the soil will respond as a displacement, and then close to failure, then the soil will be experiencing more deformations. And this is the stress strain curve. So since this is axial strain, so this is an epsilon. And if this is shear strain, you will use gamma. But this is the stress strain curve, and we talk about those like a hysteresis loop at the very beginning of this class. So those are the hysteresis loops based on lab measurements. Those tests are part of my work in grad school, and so this is a couple like loading cycles right there. So the blue one is the very first one. So the very first hysteresis loop is inside over there, and the last loading cycles when we go to failure is the red one.
So you see how the area of the hysteresis loops is like increasing. So it's, so you see like how the damping ratios is increasing, and also you can see the slope, connecting the origins and those like points right there. So if you connect the original points, so this is kind of like the origin points, and this is your first like a G max values, and then like this is so this is your G max, and now this is your the later one, G1, and then so on and so on, and this is your last. So this is 1, 2, 3, 4, 5, 6, 7 ignite, the 9 cycles of it. So this may be the G second. So first one, G1 is a G max, and each each like a loops, it gives you like a corresponding like a strain, and then like you have a pair of data, then you can establish the gradation reduction curve. But you realize that like this is triaxial, so the strain level may not be small enough, and the very first cycle that you get over there, because the strain level is high, that may not be that means like you may not be able to establish the whole curve, because triaxial data is only like able to generate like something around 10 to -2 or higher. So pretty much we are missing the data for the elastic part. We only have data from the nonlinear inelastic portions of it. And one major shortcoming of cyclic triaxial tests is what we call have the rotations of the principal stress axis, which is not well reflecting what exactly happening, or like in the field it won't happen something like this, because sigma and because like the nature of the test, your loading axis is going up and down, so which means like the end up like the principal stress and the minor stress is rotating. The sigma 1 and sigma 3 is kind of like interchanging. So if you have a sine wave, right, so this is the part that like maybe sigma 1 being the maximum, and this is being the part that sigma 3 being the maximum. So pretty much the max when we draw the Mohr circles, right, the small circles is shear stress, and this is the normal stress. Then we have our sigma 1 and sigma 3 pretty much just keep on rotating, and this kind of stress path it won't happen in the field. So this is the limitations of the cyclic triaxial test. So if you totally understand what I'm saying here, I think you are ready for your PhD level. But anyways, I want you to give you some picture or some like some ideas on what being available right out there for solid dynamic property testing. So in the future, if you guys have any project come across of those issue, I'm very happy to help out. So just make sure you give me a call, and we can set up our consultations appointment. And pretty much all my like my expertise and all my time invested on. And in my PhD studies, I also put a lot of time in cyclic triaxial tests. So this comes out from my dissertations in one of the earthquake spectra journal of earthquake spectra publications. So now this is a simple shear testing. So simple shear testing is a better way to simulate the earthquake, because your soil sample is right there, is the brown color right there, and the whole machines can shake horizontally. So it's exactly like simulating the effect. So this is a solid piece of elements right there, and when you shake, so you have a small shake table underneath here. So you kind of like able to simulate an upward propagating shear wave. So the back and forth motions, you can like more duplicate the upward propagating shear wave. And in terms of the Mohr circles, the small space, so this is the Mohr circles, like before the earthquake happens. So this will be sigma 1, or the vertical stress, and this is at k naught consolidations. The sigma 3 will be equals to k naught times the vertical effective stress. And when earthquake happens, the simple shear test in the Mohr circle space pretty much is just increasing your Mohr circle. So this is exactly how the field feel like. So this will be the stress plus the earthquake loading. So this will be the earthquake loading stress, or like it's more like a shear stress that impose on that. So pretty much like every there's a circle. So at all the stress day will be a constant of delta stress. And if this is a harmonic loading, this will be a constant. So in my PhD, I work on laboratory tests on real earthquake ground motion. So there's two different earthquake ground motion. So this is real data, real laboratory data. So we input the two different like earthquake events over there, and then we see how the stress strain response based on real earthquake loading. So that's the idea of simple shear. And again, the main difference between like cyclic simple shear and cyclic triaxials is well represented by the Mohr circles. The main difference is whether you are causing the rotations in the major and minor like a principal loading axis. And we shouldn't do that because the field it won't happen. The cyclic triaxial is an easier test to run, and many times if we are lacking of availability of the laboratory equipments, people may still want cyclic triaxial tests. And cyclic triaxial tests, we can have other usage rather than just like a site response analysis. A lot of like a pavement people, they will get the Modulus values they need. So still very popular. But simple shear test is particularly useful for geotechnical earthquake engineering purpose. And the torsional shear is similar to a little bit similar to the triaxial in terms of the setup, but instead of like going like up and down on the loading axis, you will like rotate. So and you need like kind of like a hollow samples right there. So it's a very hard to test to run, and it's not like so popular in the United States on purely just cyclic torsional shear. Rest and column, yes, we have it, but like torsional shear is a popular test in Japan. So oftentimes the way I look at it is a Japanese test, but the concept is similar in a way that you provide like excitations, a cyclic loading in torsional type of like loading. So this can go back and forth instead of like going extensions and compressions. This will go anti-clockwise and clockwise in terms of loading. So you have a motor right there to turn or to twist your hollow cell samples. So this table here summarizes like the three kind of like available cyclic testing. So all this are cyclic testing: cyclic triaxial, cyclic torsional test, and cyclic simple shear. So for triaxial tests, the main advantage is the equipment is widely available. Triaxial is very common type of testing. Many times, if you upgrade your existing triaxial test, you have a cyclic triaxial working stations, and many tests has done in the past. So you have a lot of like a data being available. The disadvantage is you cannot like duplicate like the in situ like loading conditions, which means like those like principal axis rotations that I talk about. And torsional shear tests first, like it can represent the in situ loading condition well, and the torsional test, you can go to very high strain level, and also you will be have a good control on unusual stress path. So you have a very complicated test that you want to run, this will be ideal. The disadvantage of this is like it's not uniform radial strain over the samples, because like it's hollow, so which means like so you have kind of like a specimen right there, and you have a hollow specimens. So if you just take a sections of it, so you have pressure pipe both inside and outside, and the radius from like this point and to this point are different, and same as like the way they feel about the stress. So that's why the reason they need to make it hollow is try to minimize this non-uniform radial strain problems. Again, if the whole thing is a solid, so the radial distance between the center and the outside is a lot of difference. So when you have the initial calculations, you will make a huge difference. So that's why they try to make it hollow. So at least like you minimize like the problem, but being like the innermost and the outermost, yet you still have like a radial difference. And the tall samples may allow void redistributions and non-uniform cross sections. So it's a very hard test to run and a very hard test to prepare. So usually like you cannot do it for clay, because clay comes with a block. So imagine this is ideal for sand samples, which you can reconstitute by like variations on those sand particles. And another thing is like a no bidirections loading. Well, this is truly advanced. This only for research purpose of a simple shear test. So the simple shear is well representing in situ conditions. Very nice, because it's kind of like the motions is exactly the same as outward propagating shear wave, and the most uniform stress over the samples. This one means like now you don't have a cylinder type of specimens like a triaxial of torsional shear, but you have short but wide specimens. So at least like from the vertical directions, you have a shorter dimensions. So like the stress distributions, the vertical stress distributions along the vertical directions is more uniform compared to the other two. And the cyclic simple shear, the research equipments, is available with two directions loading equipment, so which is nice. But there's also like some limitations of this type of testing. First of all is when you want one simple shear test. So this is the specimens in situ. You will apply the shear stress, right? So this is earthquake loading, loading the specimens like right there, and adjacent to your soil samples on the side, you have the counter shear stress, because like what next to your soil elements is another piece of soil, another piece of sand, and when the sands sliding or loading, deforming with each other, you will create frictions. So this part at the side, you have the counter sign frictions in situ. So this is what we call the pure shear. But in the lab, when we want a simple shear, we can impose the shear stress from the bottom of the top, and the other part of it we can have a very like a frictionals, pore stones or pore media. So you still have the frictions right there, just like the field. But the whole soil samples will be wrapped up by a latex membrane. So we are lacking of the counter stress right there. So this is smooth, while than in situ you have the frictions. So that's why like this you become like a disadvantage of the simple shear. And this problem can be minimized by having a shorter samples. So they try to minimize this distance right there, or the thickness of the samples. So this got improved on that situations. And also there's some mechanic problems, like on running the type of testing. I don't want to go too deep on that, what we call the walking issue. So for Western column tests, and again, I think this is like too advanced for this class. But if you're interested, I uploaded a presentations from NGI, from Norwegian Geotech Institutes, presented by Dr. Wuner Duvik. He was my postdoc advisor at Norway, and he did a very good presentation, the best I have seen, to talk about the Western column test. And how the math work out from calculating the G and also the D, the shear modulus and damping ratios, and feel free to read about this, and how it determines the those shear modulus and the damping values using the device, and why it called be Western columns, because the torque and when we run the tests, like the torque and the accelerations, they are Western conditions, such that we can identify the frequency, and at that particular frequency, then we can find out the values that we need. So that's the math over there. We'll talk a little bit about this, and some typical data. And this is the device of a Western column at NGI. So it has the torque right there, and also have accelerometers to measure the accelerations, and is powered by magnet. So we're very powerful magnet right there, and a couple of the electronics, and this the sensors hook up to the oscilloscope to tell you you're right at the Western conditions. So for more conditions, this is way too advanced for a master level geotechnical earthquake class. So pretty much like this only can be learned through research. But anyways, I also upload the STM standard for Western column, and I think your Quagma textbook, it did a good job to introduce the basic background on those testing. So I highly recommend you read your Quagma book as well. So for the Western columns, make sure you, if you, I don't think I will test on you, but like I may ask you some questions just like your homework, or how to correct the lab data from the field data, but I don't think I will go too deep on the details on Western columns testing. So those most commonly used like relationship for the G or G max, I think we have covered that already. Those curve is you can see from the PDF that I also like upload on Canvax. So this is the same thing that we have talked about already. And again, like if you have site-specific data, that's great. But usually, like those data obtained for field and lab testing, and only like very critical projects that you can pay a lot of money able to establish it. For preliminary design, or like for a typical project, we will use those existing available either like established curve or use empirical correlations. So if you want to learn more about like the correlations, make sure you try to study or try to look at those equations, and maybe I will try to find this paper, and then hopefully I can recover it, and I will upload to Canvax too. So for future reference, or
for your own study, not necessarily this semester. You can also like you can look at them. My expectations for this concept, you know how to use them for your project. Okay. So last but not least, the field testing. So the field testing, it has a couple very typical tests that has ASTM standard on it, which is the causal and downhole, and some CPT technique now, those advanced one, not the typical one, but the very expensive advanced one. They may also have able to measure the shear wave velocity for you, and that gives you the Gmax values. And also like even more like advanced method is those non-destructive method, the surface rays techniques. So remember, like at the beginning of class, lecture number 1, back to the beginning of semester, we talk about those surface wave, those like love rays and a Rayleigh wave. Those techniques, like they able to measure V sub S too. So pretty much like those field testing is for you to measure the shear wave velocity. So this is the idea of causal. So causal method generally you have like 2 boreholes, and then like at the elevations that you want, you would do a couple times actually. You may do like a depth here, depth here, depth there, and then do one more there. You will have a trigger, a receiver. So you will generate a signal body wave, first P wave and then S wave, right? So you can measure the body wave has 2 kinds, the primary and secondary wave. So once you like use a hammer or other sorts of excitations, you start from trigger, and then like the distance between the two, and simple enough as the concept is like you can calculate the velocity equals to the distance. So this the distance right here divided by the time. So you measure like the time that the receiver receive from the trigger. Then the time, the delta times for the wave to arrive from the trigger to receiver. Then you can calculate the shear wave velocity. So the concept is simple, but the data interpretations is very difficult, especially for P wave. S wave is easier. So those like ASTM standard, they talk a lot about the shear wave velocity, and for Gmax calculations, what you need is just the shear wave velocity. But this type of method, you also, if you want, it also can recover the P wave measurements. But in practice, like we what we need is the shear wave velocity. So that is the causal method, and there's an ASTM standard come with it. So that is some like a causal data results. So it's the harder part is the data interpretations, because sometimes the data they come out is sort of a noise that you need to like a filter, and it's may not easy to clean up the data and also to tell at which point is the arrival time. So these examples, like you send a trigger at the top at the ground surface, and then like at different like depth, you have all a series of like of a receiver, and then like or like you do this is a causal test. So you will do it one by one at different locations. Like you have trigger and the receiver, and then like through different times, then you can identify the arrival of the shear wave, the arrival of shear wave and the difference, for examples. So this is the trigger, and this is the receiver. So the time difference here is the delta t. So you can identify the arrival time. So you know the time, you know the distance, then you can calculate the shear wave velocity. And the downhole method is, so this is causal and this is downhole, because like making a borehole is expensive. So the downhole method try to cut the cost by just using one borehole. So you have the source, the trigger at the ground surface, and throughout your borehole you have different sensors, and then you have a trigger on top, and then like you know your distance from your receiver to the source of trigger. Then you can knowing the time difference, then you can back calculate the shear velocity. So that's a different like a type of method being available, and this table compare the advantage and disadvantage with the two method. So causal, like you know, is you need two boreholes. Is simple in terms of like for data interpretations. You can obtain both like a P wave and S wave, and you know you may able to get like you know another directions of the shear wave here. So shear wave, you know, you can come up with orthogonal directions. So if you have two sensors, so this is called like the top view. You can have two shear wave directions that you may able to obtain. So I'll let you to read through like this table on the difference between the two. But like you know, the cost wise, you can tell the causal method will be more expensive than the single borehole method. The downhole method will be less expensive. So for the rest of this lecture is about those like correlations of those Gmax. So we also touch base on this, and again, like you know, the details on those correlations about the shear modulus reductions and damping ratios. The better reference is go back to those files, and you know it give you like the equations, and those equations you know you actually try to understand where it come from. Is pretty much is from curve fitting method from an existing like a database like from at the Stokey lab. Those are mainly for our Western column tests. So if you are not a believer on the Western column, you know, or the Stokey type of Western columns, there's two types. There's Stokey type of a Western column, which developed in Texas, and also there's the Michigan Purdue developed the Drinovich device. You know, they don't like each other, but anyways, so this is Drinovich. So you know, that may not like you know the people like you know from the Drinovich side, they may not want to use those model. But anyways, like you know, they just have different opinions. The way I look at it, at the end of the day, is still both of them are still very good data, or very good like engineering work that like the practitioners like can benefit from. But anyways, so this is for the axial strain for the curve. So actually like the reference strain, sorry. So this Gmax equations also depends on this reference strain. So this is the G, right? So this is the G that like you want to have at the end of the day, and this is the y-axis, and this is the shear strain, the x-axis. And Gmax, you get this from the field. So this is a field measurement. I'm sorry, I have a hard time, but like you know, you understand this. So the Gmax is from the field, and A is a curve fitting parameters, and the gamma R right there is the reference strain, which is based on these equations. And this is based on both PI, plasticity index, and the stress history, OCR. And the nice thing about this Stokey model, that's you earned the Terzaghi award, is because this is very powerful in the sense that this is equations that work for both cohesive and sandy model. So he has a huge database for both clay soil and sand models, and then you calibrate it in a way that this reference shear strain can handle both soils. So if you have sand, the PI will be equal to 0, and if you have clay, then based on how cohesive your clay is, then you have different PIs, and sand will be highly depends on the confining stress. So the confining stress here will take care of it. So those are great engineering work. And very similar. This is the damping ratio curve. The D mean, he provide functions right there. Again, this work for both sand and clay, so that's why you have the confining stress and also the PI. And the D masons and other a constant depends on right there. And this reference string tied back to what you have calculated before. So and the B again is the curve fitting parameters, depends on the number of loading cycle you're looking at. So this is a very a good empirical model. It's a Terzaghi award type of model that people feel comfortable to use. And so this is I would say and so the first versions is the 2001. So those are his doctoral students, the Andeli and also the Meng. So Meng is still working at Texas with Stokey as a research associate. He has been in Texas for a long time, but his PhD work is kind of the improved versions or some modifications. So this is a Meng model, and which only work for granular soils that you can use too, and pretty much some update based on the reference strain. So these two compatible with each other. But when you have gravels, I think the Monk model work well. So the gravel data is rare, but they make it, so it's it's very great contribution. So this is better for sand and gravels. So if I have a gravel site, for sure I will use the Monk and Stokey 2003. And sand or clay, the Darren Adeli and Stokey model work well. And last but not least, those Gmax correlations, there's some older versions of models being available, but I don't recommend them, because those are a little bit outdated. The seed, he done his very first one, and other people around the world, they have some other models too, and same other other existing Gmax correlations, and if you cannot measure the Gmax values, then maybe those become handy. You can have an estimation of the Gmax, but the best Gmax value you get is from the in situ test. So you get the in situ test Gmax values, and then you use that correct for your lab data. That's your best chance to get the most precise gradation curve, and you will need those curve for site response analysis, and we'll talk about that next.